Welcome back. Hope you're doing well. We've been talking about the geometry of certain operators from Rn to Rn, right? Looking at square matrices n by n and using the characteristic polynomial in order to figure out, okay, in what directions is this operator scaling vectors? In what directions is it projecting it? Which direction is it shearing it? And all of these sorts of things. So we've been talking about the geometry in this in terms of eigenvalues and eigenvectors. Now, thanks to the coordinate mapping, we could be doing this in a more general context of abstract vector spaces as well, looking at, remember, linear operators. Remember that linear operators are functions from a vector space to itself. And the reason that we're limiting our study to these is that when we characteristic polynomial was something that arose whenever we were talking about something going from Rn to Rn. And so this is the sort of model that we want to emulate in going from a vector space to itself. We've already been dealing with only cases where our vector space domain and codomain were the same. So let's go ahead and just make sure that we get our definitions straight for when it comes to linear operators. Now, it is not necessarily true that a matrix multiplication does the trick for us in terms of these vector spaces, because in particular, we could be working with infinite dimensional vector spaces. So in general, a vector space, and let's take a vector space V and a linear operator on that vector space. And we're going to call any number lambda an eigenvalue of it if it solves the same type of equation as what we had before. Namely, if you plug vector into the equation, what you get back out is lambda times V. Lambda being kind of like my eigenvalue, my ratio of what happened before and after for my non-zero vector V. And that vector V being non-zero is called an eigenvector of that lambda, or of that map associated to the eigenvalue lambda. By the way, sometimes we'll use the term eigenfunction. Now, this will only happen if V is a functional space, such as the space of functions, the space of smooth functions, the space of continuous functions. Only then will we call these things eigenfunctions, but it's another term that you might hear us be using there. Now, if V is Rn, then we can write all of these linear mappings from Rn to itself in terms of multiplication by an n by n matrix, in which case eigenvalues or eigenvectors are exactly what we had before. They are the eigenvalues and eigenvectors of the matrix A. So let's suppose, first things first, that we have a linear operator on a finite dimensional vector space. Let's talk about what we would do here. Well, remember that we had this little picture for what we were working on before. That picture was this. We would take the vector V, and we would have a coordinate mapping to get this into the space Rn, right? So a linear mapping L taking us from V to V would then get us to this linear mapping of Rn. Well, then what we would do in order to say, okay, let's get this to be, so in order for us to be talking about things up here, let's go ahead and consider the corresponding map that takes place down here. And the way that we would form that map is that we would reverse this, go here, and compose these maps together. Once we've composed all of those maps, we get a map from Rn to Rn, and that was our way to essentially work with things in abstract vector spaces. We're going to try and build that same sort of theory here. Let's let U1 through UN be our basis for V, and let's let G from V to Rn be our mapping from the vector space into Rn. In this case, we're just going to use the same basis each time. Let A be the matrix of L with respect to this matrix. Then, whenever we're working with something going from L of this vector space into this vector space, then we can make the connection in the following way. We can look at this in terms of multiplying G of our vector V, so that's mapping from our vector space into R of n, and it's saying, okay, there is a matrix of L with respect to this basis, so it's going to be A of G of V, this G of V being something inside of Rn now, so we can form this matrix, equals lambda of GV. Maybe I don't need these parentheses here. Maybe I just need to write something like this. So A of GV is equal to lambda GV. Both of these things now being inside of Rn, since G is really not the vector itself. It's not, say, for example, if we were looking at a polynomial space, it's not the polynomial 1 plus x plus 2x squared. It's the vector 1, 1, 2. It's the vector in R3 that corresponds to it. It's the coordinates for that vector. Since we're only looking at coordinates, we're looking inside of an Rn space, and hence we can make this matrix A. Now we can talk about the eigenvalues and eigenvectors of an operator with respect to the corresponding eigenvalues and eigenvectors of the matrix A, which is exactly what's said down here. So we define that the characteristic polynomial of the matrix A to be the A coming from this to be the characteristic polynomial of the operator L. We're essentially thinking of these two things as one and the same. Whenever you have a finite dimensional vector space V and a linear operator on that space, there's a way to think of it in terms of coordinates. When you can think of it in terms of coordinates, you're back to the space that we were in our previous presentation, looking in Rn. So we can start looking at matrices instead. The eigenvalues of L are the roots of its characteristic polynomial, so it's all the same stuff as before. Let's see a couple of examples here to make sure that we're kind of keeping this stuff straight. First things first, we've got our rotation linear operator going from r squared to r squared. And let's say that r is the map that does rotation by the angle pi over 4. So what that means here, rotation by pi over 4, whenever it's not specified the direction, we are implying that it is in the direction away from the positive x-axis counterclockwise. So this is our angle pi over 4 here. Here's maybe v, and then here is the angle, or here is the vector RV. This is how this sort of stuff looks. And so the question is, given some sort of rotation like this, what are the values of v such that you get lambda times v? What are the vectors here such that when you do this rotation, you get eigenvalues or something like this? Well, I have news for us. There are none, at least not in the real numbers. In the real numbers, there are no solutions to this rotation by the angle of pi over 4. What's happening here? The idea is that we are working with the fact that not all polynomials for a particular matrix have solutions in the real numbers. If we were to go through, say, and create what this matrix was, I believe we saw something like this in a couple of videos ago. Remember that this would have been cosine of theta, negative sine of theta, and then sine of theta, cosine of theta. Plugging in theta equals pi over 4 here, we would have then attempted to try and find eigenvalues of this vector. And although we get a characteristic polynomial here, there are no real roots of this polynomial. There are no real roots for this. So if we're trying to look for things in terms of R2 and things like this for how these things are scaled, we're going to come up short. However, if we were okay getting things in complex vector spaces rather than real vector spaces, we could put in some complex numbers in here perhaps and get some answers for what we're looking for. So it's not always the case that you get eigenvectors or eigenvalues. This one has no eigenvalues and hence no eigenvectors. That's a good example to keep in mind as we go through this. It is not always the case that we even get eigenvalues and eigenvectors. And this leads us to another really good point as well. It is not always the case that your eigenvectors span your vector space. We've had that in our last two big examples from our last video. You remember we had one of our bullet points that said the eigenvectors span Rn or R3 or R2, whatever we were working in. That's not always the case. Sometimes you have no eigenvectors. You could be working in R2 and have no eigenvectors at all. And in that case, your eigenvectors definitely do not span your space. Hence, it's a little bit trickier to talk about the geometry in terms of eigenvalues and eigenvectors for those particular operators. But let's keep going here with some other examples. Let's take a look at this example. Let's try and find eigenvalues and eigenvectors for the following example. This time, let's go ahead and choose one that is a polynomial space. Let's take the map L to be the one that takes the polynomial p of x and spits out p of x plus 1. First, does this make sense as something that goes from the space of polynomials of degree? Let's say it's degree less than or equal to 3 here to try and make it a little bit nicer on us. Into the space of polynomials of also degree less than or equal to 3. This should make sense to us. Polynomials of degree less than or equal to 3, if you plug in x plus 1 anywhere that there is an x, you should still get a polynomial. The question is, what is the matrix A associated to this polynomial? What is the matrix A? Well, A is going to be determined by looking at the columns of whatever the standard basis elements of this set written in are going to be sent to. Of course, we're going to make sure everything is written in terms of coordinates whenever we write it in terms of this matrix. So we're going to want L of 1, L of x squared, and see if I can make room for it here, L of x cubed. I'll just erase it and try and give myself some room. L of 1, L of x squared, and L of x cubed. asking where the standard basis elements go in for this matrix A. Okay, so let's see what that would look like. Go ahead and use some more space down here. Actually, that space is reserved thanks to the little star there. So I'll go up instead. Let's take a look at what this matrix might look like. Or let's recall that L is going to be the one that sends polynomials x to x plus 1. So if L takes P of x and maps it to P of x plus 1, let's see what L of 1 is. Well, it's going to take every x inside the polynomial 1 and just make it 1. There's no x, so it's just going to be 1. What about L of x? It's going to take x and make it x plus 1. Know that because it's just going to plug in x plus 1 for x. What about x squared? Well, this is going to make the x plus 1 inside of the square, so this will be x squared plus 2x plus 1. And then finally, L of x cubed, that's going to make this, once I cube x plus 1, x cubed plus 3x squared plus 3x plus 1. So writing each of these in terms of their coordinates, I should have something like this. The constant term always goes as 1. The x term is 0. The x squared term is 0. And the x cubed term is 0. That's why we get this column vector here for L of 1. Then we should have 1, 1, 0, 0 for L of x, 1, 2, 1, 0 for Lx squared, and 1, 3, 3, 1 for Lx cubed. So all told, the matrix A should be something like this. Let me write it in the by column to make it so that it's a little more straightforward for me. There we go. And if we want to find eigenvalues of eigenvectors of this operator, we could go through and find eigenvectors of this matrix here. So I'm just going to take it and subtract by lambda times I. That's subtracting by lambda across the diagonal. And then I'm going to take a determinant of this value. Determinant of A minus lambda I. Well, if it's an upper triangular matrix, which this one is, then the determinant is just multiplying down the diagonal. So this is 1 minus lambda to the 4. What lambda value does this have? This has a lambda eigenvalue of 1. Notice that it has multiplicity 4 as a root of this determinant equation. So what is going to be the eigenspace here? Let's see if we can figure this out. Well, if it's going to be an element of this eigenspace, what are we going to do? We're going to need to solve the equation A minus lambda I, this time lambda equals 1, times x equals the vector 0. So we're going to be doing A minus I. Well, what is this matrix going to be? This is going to be the matrix 0, 1, 1, 1, because we're plugging in 1 for lambda throughout here. Then we're going to have 0, 0, 2, 3, 0, 0, 0, 3, and then a 0 row all the way through here. And then we're going to be doing this times, say, x1, x2, x3, x4 as a column vector. And we want this to be equal to the 0 vector. This is equal to the 0 vector. So what relationships are we going to get for x1, x2, x3, and x4? Well, let's take a look. We should get from each equation, each non-zero row, we should get an equation for each of our variables. For example, we don't get anything from our 4th row, so that's going to give us at least some sort of underdeterminedness for our equation. From our 3rd row, we're going to get the equation. That's 3x to the 4 equals, or not x to the 4, x sub 4 equals 0. Then we should get what? Something like 2x to the 2x of 3 plus 3x of 4 equals 0. That coming from multiplying through the 2nd row times this column. And then finally, we should get x2 plus x3 plus x4 equals 0. By the way, x4 is 0, right? Becomes this equation, which then plugging in x of 4 equals 0 here, that's going to give me that x3 equals 0. And then plugging both of those into this equation, I should get that x2 is 0. So I actually only have one polynomial spanning this space. It's going to be where x1 is 1. Well, what is x1? This is going to be in terms of the coordinates of P3. So this is the polynomial P of x equals 1. So this is corresponding to this vector here, 1, 0, 0, 0. So that's going to be for the space given, or the column vector that's given by here, P of x equals 1. So P of x is my eigenvector, and taking it through and putting it in here, the eigenvalue associated to that eigenvector is 1. So if I'm looking to answer this equation, I'll go ahead and just bring it down here. From our work up above, we know that lambda equals 1, and that the eigenvector associated to it is 1. Notice, again, this one we had a 4-dimensional vector space, but we could only find one eigenvalue. It did have multiplicity of 4, but it only had one polynomial in its eigenspace. So its eigenvectors did not span the entire space. A nice, interesting fact to keep in mind that we'll address near the end of today's video. But this is a neat way to think about a few different operators that we hadn't been discussing in our previous video so that we can become a bit more robust in this sort of idea. Now, first things first, the characteristic polynomial of the operator is well defined. We've been kind of working with the standard bases with these operators. But the question is, would this polynomial be the same if we were working in a different basis? What if we were working in, say, I don't know, some other kind of basis with this operator L that we were just working with? Instead of working with 1x, x squared, x cubed as the standard basis for this, what if we had done 1 plus x, 1 plus x squared, 1 plus x cubed? If we had done this basis, would our characteristic polynomial have been any different? Would we have had to change how we solved our things? And most importantly, would we have got conflicting answers from what we had just gotten with that particular basis? The answer is no. The answer is the characteristic polynomial does not care about your basis. It is always going to give you the same eigenvalues and eigenvectors, regardless of what basis that you choose. Now, those eigenvectors might be written in terms of the new basis, but once you get everything to be in the same coordinate system, it's all the same eigenvectors. So let's talk about what that proof looks like a little bit. Let's let B be the matrix of L with respect to a different basis, V1, V2 to Vn. Right, comparing this to the normal way of writing it. So let's say, for example, A is the matrix that we've been writing with it in terms of the other basis, U1 through UN. Okay, so let's say, so then we can go through and make our picture again. A picture this time coming in from looking at how we would write this in terms of two different bases. Right, we had our picture Rn, Rn, V, and V. This time we are just translating between two different bases here, this time going from U1 to UN and V1 to Vn. So here is our matrix going from, let's say that this one's going from V1 through Vn up here. And this one's also V1 to Vn. And that this is actually the map in between. This is the linear transformation that we're trying to take. This is the map from the vector space to itself that is captured by the operator L, but this time with respect to our new basis V. Well, then how would I form this B? Well, I would be going and looking at my coordinate maps, going down from here to here, and I'd be looking at this operator A. Well, if I want to solve for A here, what I would do is I would start by looking at what happens when I try and form this other direction. If I do that, then I'm going to get U be U inverse. U inverse because this is the transition matrix from the old into the new. So this is U inverse first, and then B, and then finally U. So this is the way that we would write this matrix here. A equals U be U inverse, where U is the transition matrix, in particular from the new set to the old set. Right, so that's what we have right here. So then we need to show that these two characteristic polynomials are the same. Since B is the matrix of L and A is also the matrix of L, what we're trying to show is that the determinant of A minus lambda I is the determinant of B minus lambda I for all lambda and R, irrespective of what lambda value we put in. That's our variable here. So notice that the reason that we have to set these two things equal to each other is that these both describe L. One just describes it with respect to a particularly new basis. Well, in order to do this, let's use the fact that we know how to write A in terms of B. We can write the determinant of A minus lambda I as the determinant of U be U inverse minus lambda I. But we could write lambda I differently as well. We know how that I is U times U inverse. I is U times U inverse here because, well, first of all, U is invertible. Transition matrices are singular or non-singular by definition here. And so because of this, we can write I equals U times U inverse, and we can allow the U to come, let's see how we do this here. We can allow the U to come up to the other side over here. Not on the other side of the equal sign. I should be saying instead that this is lambda I times U inverse, and that it's okay for us to move the lambda or move the U over here. That's exactly what's done in this term right there. You can see that we've just moved U inverse, which is the identity, moved the u over here to the left-hand side of this term? Well, we've got u being multiplied on the left and u inverse being multiplied on the right, so we can go ahead and factor those out on the left and on the right respectively. But guess what? The determinant map is very nice. You remember how we said that you can split up the determinant map so that if you have two things being multiplied on the inside, it's the product of the determinants, the individual matrices on the outside. That's exactly what's being done here. We break up the u, b minus lambda I, and u inverse, and take the determinant of each individual matrix respectively, multiplying those together. We know that the determinant of u inverse is 1 over the determinant of u. We can do this because, again, u is non-singular, so it has a non-zero determinant. So we can cancel these two things and just get the determinant of b minus I. Guess what? That's exactly the same equation as what we had before. We never had to specify a value for lambda. So a neat little proof trick there to show us that this is how this sort of thing works. Let's talk about some of these eigenspaces. We've already seen that eigenspaces do not have to span our entire vector space here. And it is particularly not true when our vector space is infinite dimensional, right? In fact, it can seem like a daunting task to get that many eigenvectors. So let's let L from V to V be a linear operator. And let's specify the set of all solutions to the eigenvalue equation, the L of x equals lambda x, to be V sub lambda. V sub lambda is a set of all solutions to this equation. This is the eigenspace that we're about to define, the eigenspace of this operator with respect to the eigenvalue lambda. Of course, what we want to make sure is that we're not including just an eigenvalue here or an eigenspace. We're not calling something an eigenspace if lambda is not actually an eigenvalue. So we go through and make sure that we're saying that lambda is an eigenvalue of L if and only if this set of all solutions is non-trivial. It contains more than the zero vector. So if it ever contains more than just the zero vector, that's when we're going to call it the eigenspace of our operator L. By the way, this is still a subspace for the same reason as the matrix was a subspace before. It is the kernel of a linear operator. And we discussed in a couple of videos ago that the kernel is itself a subspace, L of x minus lambda x. So this is a kernel of this particular operator. All right, so let's go ahead and see some examples with this one. This time looking with functional spaces like smooth functions here. V is C infinity. D is the differential operator, taking a function f and popping out its derivative once a function is plugged into it. Now let's think about what it means for a function to be an eigenfunction of this operator. An eigenfunction, remember, means that if you plug something into the vector itself, you're going to get a scalar multiple of it back out. Well, what is d of f? D of f is given as this formula, f prime. This is a differential equation. We are looking for an equation. Sometimes you would see this instead of written as f here, you'd see it written as y prime equals lambda y. We are trying to solve this differential equation here. Well, you remember how we would do this, right? We would go through and we would say, maybe we can do this down here. We would say we have y prime equals lambda y. So we would go through and divide by, let's see, we would say this is dy dx equals lambda y. And then we would write, because we can think of these things as being moved over or use the definition of differentials in this way, we could write this as 1 over y dy equals lambda dx, and then proceed to integrate both sides. And we would get what? That this left-hand side is the natural log of y, and that this right-hand side is going to be lambda times x plus some constant, and then we'll call that constant c. And then we would go through and solve for y by exponentiating on both sides. So we would have e to the this. That would give us that this is e to the natural log of y, which is just y, and that this is e natural log of x times e to the c, which is itself a constant, and we can just write it as c. So y equals c times e to the lambda x. So going through and saying, how do we get this value of y? We could use a differential equation technique to go through and solve that. Indeed, whenever we have this, we get f prime equals lambda f of x. So it follows that f of x equals c times e to the lambda x, where c is a non-zero constant. Why are we specifying non-zero here? I didn't see that anywhere in my solution from before. The reason we specify non-zero is that if it is zero, our function is the zero vector. The only thing that we want to have be our eigenfunctions are those that are non-zero. So we go ahead and throw out zero from our set there. Notice, by the way, we never did have to solve for lambda in the midst of all of that. That means that lambda wasn't any lambda in the real numbers is an eigenvalue for D. The corresponding eigenspace is the one that is spanned by the eigenfunction E lambda x. Let's think about what this means. We've just seen a lot of eigenvalues. Before, we would only find at most n because we were working on n by n dimensional spaces. We have just found a number of eigenvalues that is certainly infinite and, in fact, equal to the cardinality of the real numbers, which we may know is uncountable. So the corresponding eigenspace spanned by E lambda x, all of the things that we're about to talk about are also true, that these things are linearly independent from one another. We'll talk a lot about each of these, but this is going to be a lot of functions for us, a huge number of functions, a lot of eigenvalues. It's a kind of a crazy amount of data getting from how this sort of stuff works. So what the differential is doing is in some sense scaling by how much you're going in the direction of E to the lambda x for each lambda. And how much are you scaling it by? Well, the coefficient of lambda. So that is kind of describing the geometry going on here in what is known as an infinite dimensional vector space. Geometry in these things is extremely wild and honestly a lot of fun. So let's see another example here. Let's take a look at a double differential operator, or just the twice, taking the derivative of a function twice. That's like that function L for this same space. Well, if we're going to be doing this, then we're solving a differential operator again. You may be familiar with this differential equation thanks to the auxiliary equation, right? There's our notion of, I think, what was it called, first order differential equations, what we could use auxiliary equations for and solve for specific values of m, which give us specific types of solutions to the homogeneous equation given here. In this case, this is only the homogeneous equation, so we don't have to worry about any particular solution in this case. For this one, let's not worry about that for now. Let's go ahead and use the fact that if we note that L is decomposed with itself, D being our operator from before, L is decomposed with D. Hence, whenever df equals mu f, we know LF equals mu squared of f. Well, we know what the formulas look like whenever we take the first derivative. We know that those look like the following. We're going to get that df equals mu f. We know that that's going to be what? F is equal to e to the mu x times some constant c. Okay, so f is going to be c times e to the mu x. So what is L of f going to be here? Okay, what is it going to be? Well, it's going to be written in the following way. We're going to try and get LF to be all mu squareds of f. In the case that mu squared is real, which is what we want, what values of mu would work here? What values of mu squared would work? Well, let's say that, for example, we get the corresponding eigenvalue of L here, and let's say that lambda is going to be some sort of real number. What mu values would work? Now, there's different cases here. There's cases that are different here whenever we're considering lambda being greater, less than, or equal to 0. Let's talk about each of these cases right below here. Let's talk about the case where lambda is greater than 0. Okay, if lambda is greater than 0, that is the eigenvalue for this space. Here again, lambda equals mu squared here. Then what is mu going to be? Well, mu also has to be greater than 0, right? Well, not necessarily. Mu could be a negative number. Well, and it can't be 0. So mu is going to be either less than 0 or mu is going to be greater than 0. Either way, we know exactly what type of formula we're looking at. We're looking at e to the mu x as our spanning function here, right? E to the mu x. All right, so e to the mu x is going to be one of our possible spanning functions here, right? E to the mu x. Now, here we're defining mu to be the positive square root of lambda here. So we're also going to make sure that we're including things like e to the negative mu x. If lambda is specified, then these are two different functions. Both of these values square to give me lambda. So I'm going to have two different functions here in my space of eigenfunctions, e to the negative mu x and e to the ux. The span of these is going to give me my eigenspace for lambda, right? Which is, as we've said, this is mu squared. So in particular, mu is the positive square root of lambda. So that was the case when lambda is greater than 0. The reason I specified lambda greater than 0 is that lambda less than 0 with this equation is going to look a little weird. What mu values are we looking at if mu squared equals -1, for example? We are looking at imaginary numbers for mu. So we need to make sure that we are kind of taking some care when it comes to that. So we're going to have the same sort of span, but this time it's going to be out of the functions like e to the negative, let's see, mu is square root of lambda. So we're just going to say e to the negative mu I times x and e to the mu I times x, something like this. This is our new span here. Now, these functions can be written a little bit differently. You may be familiar with these in terms of the following expansions. You might be familiar with these as cosine mu x plus I times sine of mu x. That same thing right here. You might be familiar with these as cosine ux minus I sine mu x. Either way, we have two different functions here that we could write a span with respect to. So this is really equal to the span of cosine of mu x and sine of mu x. Because this is a linear combination of two more basic functions than the ones that I have written out here. Cosine mu x and sine mu x are what both of these functions can be written in terms of. And this just looks a little bit simpler. In fact, we're going to prefer this sort of notation for lambda is less than 0. For lambda equals 0, we're looking for all of the values such that whenever you take its second derivative, you get 0. And what are the functions that span the following space? If the second derivative equals 0, then you're looking at the functions 1 and x. And we can just kind of do that one by inspection. 1 second derivative is 0, x second derivative is 0. The same cannot be said for x squared. Notice, by the way, that these are all eigenspaces of dimension 2. Right? There are 2 functions in the span of each one. Remember, if you fix a lambda, mu is predetermined to be the positive square root of lambda. So this is just 1, 2 functions inside of here. This is 1, 2 functions inside of here, no matter how you write it, this one or this one. And then this one is also 2 functions. So each of these has a span of 2 inside of its eigenspace here. Okay. So let's go ahead and just have that all revealed here, that this is what we got from that. U here is going to be the square root of negative lambda, which means we're doing I times the positive square root of lambda whenever we write this. So this is the way that we can write each of the eigenspaces for this particular linear operator. Okay. So really interesting things here, especially since this one ended up having lots of different types of eigenspaces together with the different cases of eigenvalues that we came apart. One thing to keep in mind, maybe before we move on here, how did we know to go through and do it this way? How did we know, for example, that we wanted to work with df mu f instead of just working straight with L? The answer is we did not have to. Because we know how to use auxiliary equations on equations like this, we could have just used auxiliary equations and treated this like a differential equation. That was another way to do this. If we had used auxiliary equations, we would have gotten these exact same answers. In some sense, the way that we did it derived where those answers came from. That is coming from the differential operator D, rather than just straight up using L. Now, the thing that kept me in mind of like thinking, okay, I need to be breaking this up into cases, was that I noticed that I was able to get any real value for the first operator, but that I was about to have to set whatever my value was in order to connect things from D into the differential operator for L. I was about to have to connect them in this following way. So given a lambda value L, or a lambda value, which I would expect there to be solutions for regardless, I was going to have to solve for mu. Well, this ends up being real or imaginary depending on where I'm at. So I could have had e mu x, e to the negative mu x right here, or I could have had e to the I mu x, and that would have just been a different formula, and then e to the negative I mu x. And then finally down here, I would have had different formulas as well. So it just told me that whenever I plug in different values, I'm going to get different formulas. So I just had to be a little bit careful about that. Let's go through and see a few propositions with respect to linear operators now. Indeed, now that we're discussing abstract vector spaces, we can say the following propositions whenever we're talking about finite dimensional or infinite dimensional vector spaces. So let's take a look at this first one. If you have a vector which is an eigenvector of your operator L, then the associated eigenvalue is unique If you have one eigenvector, you can't have two eigenvalues for that vector. Let's suppose it happens. Let's suppose you get something like this. LV equals lambda 1v, LV equals lambda 2v. We're about to run into a wall, and I think we see that here. We could get to set both of these two things equal to each other. L1v equals L2 times v. Well, if I go through and write this stuff together, I'm going to get L1 minus, or lambda 1 minus lambda 2 times the vector v equals the 0 vector. And since v is not a 0 vector, that means lambda 1 minus lambda 2 equals 0. And that gives us that the two eigenvalues were actually the same. This is neat because it tells us that eigenvectors or eigenspaces are in some sense separated by their eigenvalues. In fact, we could say more on that line. Suppose you have two different eigenvectors associated to different eigenvalues. Then those vectors are not only separate, they are linearly independent. Let's take a look at what that proof is for just a second. For any scalar, the vector t times v1 is an eigenvector of L associated with the eigenvalue lambda 1. Now, lambda 2 is not equal to lambda 1, which means that you cannot have that v2 is a scalar multiple of t times v1 thanks to proposition 1. That is, the vector v2 is not a scalar multiple of v1, so v1 is not a scalar multiple of v2 by vice versa, dividing by t, and hence that's exactly the statement. The vectors v1 and v2 must be linearly independent. The question is, we did this for one vector, we did this for two vectors, can we do this for three vectors? You better believe that we can. If you have v1, v2, v3, different eigenvectors associated with different eigenvalues, they also end up being linearly independent. We are about to establish a process by which we can continue on by induction to do this for any number of eigenvectors and eigenvalues. Let's see how this little bit of an inductive step works here. So let's suppose, first of all, that we have some sort of linear dependence relationship between these two vectors. And let's show it to be the trivial one, namely the one where t1, t2, and t3 are all 0 for the scalars associated to these vectors here. Well, then if this were going to be equal to 0, well, then the linear operator would respect that. It would also send that to be 0. And we could use linear operations in terms of L to get that this is all just a span of specific eigenvectors, because v1, v2, v3, we start being eigenvectors associated to all different eigenvalues right through here. Well, it's going to follow that. I'm going to go through and subtract by a multiple of this vector right here. I'm going to go through and subtract this left-hand side equation by lambda 3 times this vector. Well, this vector is 0, right? So I am just subtracting by 0 when I do this. But when I write it like this, look at what happens. Here's lambda 3 times the 0 vector. This is the 0 vector written as this. So if I write it this way, then it turns out that because I multiplied times lambda 3 here, I'm going to get a term that cancels. This term is going to cancel with this term. Now I'm going to be combining these two terms together and these two terms together in this next step. That's this step right here. I'm going to combine them in the following way. Anything with a t1 in it, I'll go ahead and factor it out. And then I'll factor out the v1 as well, and I'll just be left with lambda 1 minus lambda 3. Same thing with my second term here. I'll factor out t2 and v2, and I'll be left with lambda 2 minus lambda 3. Notice, by the way, that these are not 0. Lambda 1 is not equal to lambda 3, and lambda 2 is not equal to lambda 3. And that's by the fact that these are distinct eigenvalues. So, interestingly enough, this ends up being a way of writing two non-zero vectors in terms of specific scalars equal to 0. This time it's two vectors, not three. But we know that any linear dependence relationship between two vectors from different eigenvalues must be a trivial relationship. These two vectors are linearly independent. So by the above, that is from proposition 2, v1 and v2 are linearly independent. What does this mean? That means that t1 and t2 must both be 0, because these certainly aren't 0, so t1 and t2 must be. Well, then there's no way to get t3 times v3 equals 0 other than just saying that t3 equals 0 as well. And since all of our scalars are equal to 0, we get our results that this is a linear independence relationship. So we could then continue on to prove our theorem with respect to each of these, v1 through vk. If these are eigenvectors of the linear operator associated with distinct eigenvalues, distinct being operative here, you saw where that was useful in our proof before, then v1 through vk are linearly independent, right? So this is saying, for example, if you are in a, say, a finite dimensional vector space, so let's go ahead and take a look at this one down here. Let's take a look at corollary 3 for just a second. If you are in a finite dimensional vector space looking at an n by n matrix, and you figure out that you have n distinct real roots for that, that means you have n distinct eigenvalues. Each space has its own eigenvector. Well, how many eigenvectors are there? There are n of them, and they are all linearly independent, thanks to our previous theorem. Well, if they're all linearly independent, that's a maximal linearly independent set because you have an n-dimensional space. Hence, that thing is a basis. So Rn has a basis consisting of those eigenvectors that you just found. What I talked through is essentially the proof. Any lambda I is an eigenvalue of A. Each one gets an associated eigenvector. Those vectors are linearly independent. Therefore, they form a basis. So neat thing about connecting this back to finite dimensional vector spaces. If you have n distinct eigenvalues, your vectors do indeed form a basis. Your eigenvectors form a basis for that. But let's talk a little bit about these other two corollaries before we conclude here. First, if you have distinct real numbers, lambda 1 through lambda k, then the functions e lambda 1x, e lambda 2x, and e lambda kx, these are all linearly independent. How do we know that? Doesn't seem like there's any sort of eigenvectors, eigenvalues operators going on here. But wait, these were eigenvectors for us just a second ago, weren't they? They were for the operator d, that is the operator df equals f prime. These are eigenvectors, and guess what? Each one was associated to a different eigenvalue, that eigenvalue of lambda 1. That's exactly what's said here in the second sentence. Each of these are eigenfunctions of the linear operator d associated with distinct eigenvalues lambda 1 through lambda k. Well, because of that previous theorem, these all have to be linearly independent in this space. All of them, the only way that you can make them all add up to be equal to 0 is if you just put scalars of 0 in front of all of them. One more corollary for us here, corollary 2. If v1 through vk are eigenvectors of a matrix A associated with distinct eigenvalues, lambda 1 through lambda k, then the v1 through vk are linearly independent. Going back to our finite dimensional stuff there, if we had, instead of a linear operator, we were working with a matrix, then if you have k distinct eigenvalues, then the respective eigenvectors are also linearly independent. All right, so a neat little thing today about how we treat linear operators as almost identical to how we deal with things in terms of Rn. Namely, we are able to use the coordinate mapping to convert any element inside of our abstract vector space into a space like Rn. And then we can use eigenvalues and eigenvectors of a matrix to determine the geometry of these sorts of operators. But that'll do it for today. Thank you so much. Have a wonderful day.